Hi guys, in this video we're going to be looking at de Moivre's theorem, which is really just an extension of the multiplication rules for polar form. So if we start off thinking about a value, just any complex number z, which has a modulus of mod z and an argument of theta, then that would be mod z cis theta. Then we want to think about what happens if we do z squared. Well, that's just z times z. Which is mod z cis theta times mod z cis theta. And if we use our rules that we learnt for multiplying complex numbers, then that just means that we're going to multiply the moduli and add the arguments, which in this case, because these two are the same thing, gives us mod z squared as our modulus and 2 theta as our argument. So there's kind of a bit of a pattern there. We squared it. We ended up squaring the modulus and doubling the argument. So let's just see if that pattern continues for cubing. So z cubed, we could write as z squared times z. And if we take our result for z squared from above, we can substitute that in. And again, we see that the same pattern plays out. We're now cubing that modulus and we're multiplying the argument by 3. So de Moivre's theorem basically just extends this to any values. And so it says that if z is mod z cis theta, then z to some power n is equal to the modulus of z to the power of n. And then cis, and then the argument will be n times whatever theta value you started with. So it's really quite a nifty theorem because suddenly we can raise complex numbers to powers. Now the other really cool thing about this is it doesn't just work for integers. So the examples I showed you before, n was always an integer. Turns out n actually works for any rational numbers. So q, remember, means rationals. Rationals are any numbers that can be written as a fraction, where you've got an integer over an integer. So that means it works for negative numbers, fractions, basically any sort of power that you'd ever want to do. So we can easily do things, we could do z to the 5, but we could also do z to the negative 3 or z to the power of a half. Z to the power of a half, by the way, is the same as taking the square root of z. So we can take the square root of complex numbers really easily. We could do z to the negative 4/3 if we wanted to. Whatever, as long as it's a rational number, we can do that power. So it is a really, really useful theorem for us. So I'm just going to show you a quick example of using that theorem. So here we've got a complex number in Cartesian form. 1 take root 3i, and we want to raise it to the power of 6, although I'm actually going to change that to 7, just to be annoying, because I ended up doing the working out for 7. It's a bit more interesting. So what we've got to do first, I guess, is put this into polar form. Now, you've got 2 options for doing that. You can use your swanky graphics calculators, or we can go back to basics and draw a little picture and say, okay, well, if 1 was there and square root of 3 was down here, this is going to be my angle theta. So I could do theta and then use your calculator to do tan to the minus 1 or arctan of root 3 over 1. You would then get pi over 3, but because we've gone backwards around the unit circle, it's going to have to be a negative pi over 3. And then to get our modulus, we would do the square root of 1 squared plus negative root 3 squared. That's going to give us the square root of 1 plus 3, which is root 4, which is 2. So putting this into polar form, we're going to end up with 2 cis negative pi over 3, all to the power of 7. Now this is where de Moivre's theorem comes in. So what we're going to do is this 7 is going to become the power on the 2. Okay, that bit's easy enough. And then we're going to multiply the 7 by the angle. So it's going to become 7 pi over 3. So this is where we're using de Moivre's theorem. And sometimes you'll just see that written as dmt. Okay. 2 to the power of 7 is 128. And then with our negative 7 pi over 3, what we can do is we can go, okay, well 7 pi over 3, that's actually a full lap of the unit circle in there. Because if we break that up, we can break it up into negative 6 pi over 3, take another pi over 3. And 6 pi over 3, that's just the same as 2 pi. So if you remember, one of our rules for simplifying cis is that if you've got multiples of 2 pi, you can just cancel that down. So that's just going to become 128 cis negative pi over 3. And if we want to go to an exact value and fully expand that, then we can do 128 times the cos negative pi and 3 plus I times sine of negative pi over 3. The cosine of negative pi over 3 is a half, and the sine is negative root 3 over 2. So if we expand all of that out, 128, if we halve it, is 64. Don't want to positive there. It's actually going to be a negative. So it's going to be take 64 root 3 I. So that would be in exact form. Okay, I hope that makes sense. There are some questions to do along with that. And please ask away if you've got any questions. Thanks for watching, guys.